Yes. Good morning. Welcome. I see some people to whom I've not been formally introduced. So let me. So I'm Jaikumar Radhakrishnan. But our speaker today needs no introduction. So we are very happy to have Madhu Sudan from Harvard University, an old friend of our department. Probably he gave a talk in this room 25 years ago. He's going to speak today on streaming CSPs.
Great, thanks. I don't know what's better if I take off the mask and it'll be more audible. Okay, sounds good. All right, so so this is a talk on some new work that started because my current student, Santoshini Velusamy, started some work when she was an undergraduate and working with Ameya Velinkar and Venkat Guruswamy on streaming CSPs. And then she roped in Chini Chow and Sasha Golovnev, who were both at Harvard. Chow is still there, and Sasha was a postdoc there, and now he's at Georgetown. And the three of them were trying to get some extensions of their results. And then finally, we after that, they roped me in, and I started working with them. And now we have a broad collection of results on streaming constraint satisfaction problems. So I'll tell you what streaming CSPs are and a little bit of background, and then tell you about our results. Actually, I don't think we're going to get to future directions. So, all right. So first thing I want to say is we're not going to be talking about any one single computational problem, but an infinite class. So what do we mean by an infinite class here? So each problem in this class is given by a finite family of finite functions. So these are the constraints that you're allowing. These constraints will take a constant number of variables, k variables. Each one of these variables can take a constant number of values, q values. And given an assignment to some tuple of k variables, this function f of f will tell you whether the constraint is satisfied or not. So depending on what family f I work with, I get different constraint satisfaction problems. And what's a typical instance of a constraint satisfaction problems? There are some n variables, m constraints, think 3CNF or something like that is very familiar. Other examples we'll talk about in a couple of minutes. A constraint comes in the form of saying, take one of these families, functions from your family, apply it to a particular sequence of k variables, and these k variables can be arbitrary, they can be repeated across constraints, but within a constraint, they have to be distinct, okay? And then we will say, well, okay, try to satisfy that constraint, and you have a whole collection of m constraints, so your goal is to satisfy the maximum number. Today, we will often talk about the maximum fraction of satisfiable constraints. All right. Example problems that fit in this framework, maximum cut, maximum die cut, are all very simple natural problems. So for example, maximum cut will say, assign every variable a 0 or a 1. And then there'll be lots of, so this is the variables will correspond to the vertices of a graph. The 0, 1 labeling says, are they on the 0 side of the cut or on the 1 side of the cut? And then every constraint will say the XOR of the two endpoints should be 1. So constraint is satisfied if it crosses the cut. Constraint is not satisfied if the edge does not cross the cut. And you want to maximize the number of satisfied constraints. You can also have directed cuts and other such things. If you want to do things like maximum SAT, 3SAT, or exactly SAT, or Q colorability, they can all fit in. But to describe SAT, I'll need some 11 functions, very crudely counting. Maybe I can minimize it a little bit, but it'll be a whole collection of different functions in this finite family. Okay. So there can be many different things. For the most examples we'll think of a single function. The results carry over to multiple functions. A special case that we will talk about, maybe not so much, so maybe I will just skip the slide and jump ahead. All right. Okay, so today we're going to talk about streaming solutions to these problems. So in streaming, the input comes along as a stream, and you have a limited space in your algorithm to try to remember what part of the input you've seen, what's the input that you have seen, and you're trying to make decisions on the fly. We won't care about any intermediate state of the algorithm. It's just that at the end, you should be reporting the maximum fraction of satisfiable constraints. Okay, so the constraints will come streaming along. You already know, let's say that there are n variables and each constraint will come along. And then at the end, you have to answer the question, what's the maximum number of things that are satisfied? Since exact computation is hard, we will often talk about approximate solutions. When you're talking about approximate solutions, algorithmically, people, what they want is what's called an alpha approximation. You output some number V, which is upper bounded by the actual optimum, but also lower bounded by alpha times the optimum. So alpha is going to be a number between 0 and 1. And the closer it is to 1, the better your approximation. But we will try to ask the question, what's the largest alpha you can get? In this talk, we will actually talk about a much more refined notion. These are gapped promise problems, as they're called. We will only ask you decision questions. We will give you a promise that either gamma fraction of the solutions are satisfiable, gamma for good, or beta are satisfiable, beta for bad. And can you distinguish between gamma, at least gamma, or at most beta? And the ratio between gamma and beta is roughly the approximation ratio that you're shooting for. You have to do the minimums and the maximums in the right places. Okay. All right. So questions, yeah.
So when you say the constraints from one at a time, so the function is presented and also the variables that plug into that function is presented at the same time.
Exactly. Each constraint comes along. This is the function applied to these variables in this order.
So it's about that will be specified by the k log n bits.
Each constraint itself is about k log n bits, exactly. And overall, if you have m constraints, so this is like m k log n is the input size. For the most part, we should really think of m and n as being the same, because for approximations, if you have many more constraints, you can just subsample away. And if you have fewer constraints, it's still an interesting question, but n is still sort of, for lower bounds, we will want to work even when m equals n, and then we'll be able to prove lower bounds in that case. Other questions? And yeah, definitely feel free to interrupt and ask questions.
How to do exact sort of like the problem of solving the CSP? Is it you?
Sorry, if you want to do exact, what is the question?
So I want to maintain a solution, full solution to all the causes.
Right. So two things. One, we will never even be talking about returning a solution because we won't have enough memory to remember the entire assignment to n variables. We'll typically be thinking of much less than n space. And the other thing is that, yeah, I mean, you might want to say, can you actually compute the number exactly? At the very least, we know this is NP hard, so that should mean something, but formally it doesn't mean anything. Today we'll be talking about unconditional lower bounds. But on the other hand, and we will only be restricting the space and we'll allow the time to be arbitrarily high. So NP hardness does not mean anything in the setting, but still, yeah, I mean, it's pretty easy to see that actually exact solutions are going to be pretty hard, even in the space bounded setting with unbounded time. Okay, so in fact, here's an example. Okay, here's a max cut instance, and you are trying to simulate the algorithm. Okay, so tell me what's the size of the max cut in this graph? So this goes on. I mean, I've seen Jelani do these things with streaming algorithms where he puts fruits into a basket and removes them and asks you what's the name of fruit which is actually in there. I mean, these are impossible. I mean, streaming, the honest answer to every question should be cannot be done. Okay, that's first approximation to every question. But actually what happened was in 2011 in the Bertinoro workshop, they finally realized that actually nobody had looked at streaming CSPs. So for whatever reason, we somehow forgotten to pay attention to this question. But you just saw this max cut example streaming by. By the way, I don't know if anybody got a chance to think about this while we were flashing these edges. This was a bipartite graph. Okay, so this was a max cut value is 100%, but actually the cut is not obvious, and at least I try to hide it.
What
What I did-
time was unfairly constrained, not just the space, but the time was unfairly constrained.
you should take place of a router in the internet, okay? And then you'll not be complaining now. All right, so we realized, oh, we don't know anything. In 2015 to 19, one problem actually got a significant amount of attention. There was some work that I did with Sanjeev Khanna and Michael Kapralov, and then with Velinker, and then there's a beautiful work by Kapralov and Krashen. That's a really amazing piece of work. Technically, it's phenomenal. And what they show is, complete proof for what we were not able to do. I mean, justification for what we were not able to do. We had this graph, and we would have wanted to say, is it max cut value 100% or 50%? We can't tell the difference. And that's really the truth. Every graph has a max cut value of at least half the edges. So if you can count the number of edges, then you can output half that number, and that's a pretty safe bet. But doing anything better than that actually requires linear space. In our early papers, we could only show that this required square root of n space, and many of the results today are going to be about the square root of n space lower bounds. And but Kapralov and Krashen showed that actually even n space will not give you anything better. Okay. All right. So that is a great technical result, completely unsurprising to me. What's actually very surprising to me is this paper of Guruswamy, Velinker, and Veluswamy, who say that actually there are non-trivial algorithms in this space. Okay, it's very surprising to me that when this graph is streaming by, and you barely have sort of time to understand what, where the cut could be, etc., you can actually do some non-trivial things. So max cut, what would we say? The graph could be bipartite, or the graph could be a random graph, and you can't tell the difference. That's really what the result of Kapralov and Krashen, for instance, proves, more or less. Okay? Slightly not exactly random, but still. If you consider the analogous question, there is a graph in which all the edges are going from left to right, or there is a graph in which is completely random. Can you distinguish the two in the streaming case? The answer is yes. Okay, and you can do a lot better, and you can get, even if it's not 100% versus 25%, a random cut will cut 25% of the edges in a directed sense. You want to have the edges going from left to right. And you can distinguish those two, you can do a lot better. So I'll talk about this algorithm because I find it very surprising. Then with Chow and Golovlev, they extended it to, they got the optimal result for die cut, and they also extended it to maximum satisfiability and other problems. So some other problems also have some non-trivial approximations, not just, you cannot distinguish between random and worst case, okay, or best case in this case. So what I'll talk about most today is what we call a sketching classification, which reminds me that I forgot to tell you, whoops, I have to go through all of these slides. Sorry, I think there's a better way to do it, but I will. All right, maybe I should do the better way.
Too frustrating.
This is too frustrating, that's correct. So, okay, so I'm going to be talking about results in a special setting, which is called this sketching algorithms. So sketching it's a space-bounded algorithm. It's a restriction of streaming algorithms. But the sketch have a nice composability property. If I take a stream divided into two pieces, and I say, tell me what is the state of your algorithm after seeing the concatenation of the two streams, you should be able to tell me what it is by being told what is the sketch, a summary of the first part and the summary of the second part for any arbitrary decomposition. This makes algorithms restricted, but almost every algorithm that we seem to know are sketching algorithms. A lot of the algorithms work in the following framework. You have some big vector that you actually want to maintain, but you don't have enough space to maintain it. Okay? Some huge vector. What do? Instead is you multiply it by some carefully chosen matrix, maybe from a small random space. And instead you maintain the small vector A times V. And A times V is often sufficient for whatever computation you want to do at the end. Because this is a linear projection, if I want to sort of consider the state, which is the sum of these two state vectors, all I need to do is compute A times V, if this is V and this is W and this is A times W, compute the two and then add them up. So most algorithms work in this sketching framework. Those are the only ones we are able to rule out. The reason we are only able to rule out those is because of some technicalities. We are not able to get, well, it's not, sorry, it's a there is a technical barrier over there. It's not merely a technicality, but that's the best we can get to. Okay. All right. So, so today I'll try to tell you about the sketching and sketching complexity of all CSPs and what we can say about them. Exact characterization in the sketching sense. And mainly we will actually get a dichotomy. So let me tell you a little bit why we actually studied CSPs. Why do people like to study CSPs? There's some natural interest. There are problems like maximum cut, maximum die cut. Unique games is a constraint satisfaction problem that's pretty popular nowadays. Maximum colorability is like this. But the reason you usually study CSPs is not because of the interest in specific problems, but because you can study an entire class and get tight results everywhere. Okay, the possibility exists. It's not going to go through Lardner's theorem or some such thing which says this, oh, there'll be like all kinds of intermediate levels of complexity. You'll get a very clean separation. And when you get clean separations, you can sort of look back and say, okay, I know that there are algorithms out there, but there's only a finite number because we've only had finite time to explore this infinite class of problems. We could have only discovered finitely many algorithms. So what are the algorithms? It turns out that actually in the case of CSPs, norm approximations turn out to be very, very useful. And that's how we'll approximate die cut, for instance. There are some other things which we see utility of, or we sense utility of, but we are not able to prove. You can do some random walks on graphs. And if you have a general constraint satisfaction problem, there's some underlying hypergraph, and you can do some walks on those, locally explore how the constraints interact with each other. And it gives you some potentially useful information, but we don't know how to prove much about those things. There are also all kinds of snapshots you can come up with saying, oh, this is what my graph looked like in the end, which is surprising that you can get to that state, but you can. But then we don't even know what else can you do with those things. So there's some further room for exploration over here. But there's basically still a handful of algorithms, and those are it. You also see that, you never see a problem which can be solved with 2 to the square root of log n space. It's a legitimate space restriction. You either get polylog n space will suffice, or you need at least square root of n space. Why this dichotomy? Well, you don't see this naturally in streaming, and in CSPs, you can actually prove such results. So that's part of the reason why we tend to study CSPs. It was the same reasoning that we used for when we were studying approximation in the polynomial time setting. Now we can study it in the space bounded setting. So what are some results that we have? So there's an entire dichotomy for sketching. There's also, we actually get non-trivial algorithms for infinitely many problems. So many of these problems where you can say, oh, let's consider the optimum, the sort of satisfaction being 100% versus random. You can get algorithms which will definitely distinguish those two and then do more. So there are lots of algorithms, which is a bit surprising. And I'll show you the algorithm of the previous work, the die cut algorithms, and saying that they will be able to generalize to a large class of CSPs sounds a priori not so immediate, but it turns out they do generalize. And then whenever we get these things, we get square root of n lower bounds for large classes. Some of these lower bounds are not just for sketching, but for all streaming problem algorithms. Sometimes we are actually restricted. Even the cases where we say, well, we tried the sketching-based algorithms. When they fail, you don't get, and when they work with polylog n space. When they don't work with even square root of n space, and even when you allow much more flexibility like streaming. So
question, so when you say dynamic CSPs, do you mean the same thing as streaming CSPs, or?
Yeah, so dynamic, sorry, I should have really killed this thing anyway, but this was okay. Let me actually strike this thing because
One can imagine a dynamic version by trying to maintain the solution to an instance that's changed.
That's what I did mean. The instances you are inserting and deleting things. When the algorithms work, they actually work with the insertion and deletion framework. There was a result in the literature which seemed to suggest that streaming algorithms have to be sketching algorithms when you're inserting and deleting, but that result is very sketchy. So I don't trust it. I mean, there's nothing wrong with the theorem. It's just that when you apply the theorem to any particular case that you care about, you realize they're ruling out things that you didn't really care about. So they will insert in n variables 2 to the 2 to the 2 to the n clauses, and then delete 2 to the 2 to the n clauses, and then they'll say that log n space is necessary. Well, by the time I inserted the same clause 2 to the 2 to the n times and then deleted it so many times, I need that much space to count the number of times this clause was inserted. So it's not very interesting results out there. All right, sorry. That should not have been there. I'll scratch that from in the future. We also get a significant extension of the linear space lower bounds of Kaprilov and Trachun, but I won't talk about that today. I'll just talk mainly about this broad classification, which is tight for everything. Okay. All right. So now let me jump into the algorithms. Yeah.
I have a question.
Yes.
So you said that you have non-trivial algorithms for infinitely many dynamic CSPs. So what does infinitely many mean here?
So there are infinitely many different functions f, for which the corresponding optimization problem has a non-trivial algorithm.
Okay.
So I'll give you an example so max k and for every k, and there are infinitely many different k's. So each one of these has a non-trivial algorithm.
Oh, okay, cool. Yeah, thanks.
Great. Okay, thanks. Jayakumar, yeah.
So the result of linear space for half plus epsilon approximation. Yeah. I mean, technically the input is of size n squared. So is it likely that there will actually be an n squared over?
Good. So the input for max cut could be of size n squared, but if you are going to so could there be an n squared lower bound? No, because what you can do is the following: as the since we're not looking at time constraints, as the graph is coming along, you sample away n over epsilon squared edges and only work on this subset of edges, and your max cut value on the sample will be as good as the max cut value on the whole graph. So n over epsilon squared space should be sufficient even to get 100% approximation, 1 minus epsilon approximation. Thanks. Any other questions? All right, so let's now talk about an algorithm in this space. So I'll start with the algorithm of Guruswamy, Velinkar, and Velusamy. And what they define is this quantity, which is very natural in the context of directed cut. You look at every vertex and define its bias. And the bias is of this vertex would be 2, which is the number of edges coming in minus the number of edges going out. So -2 maybe. Okay. So for each vertex, you associate a bias, which is how many edges are coming in and how many edges are going out. And the bias of the graph is half of the sum of the biases, but the absolute values. If I just summed up biases, actually, I'll get 0. But I sum up the absolute values of the biases of the vertices. Okay. And what do we want to think about? Think about a graph in which all the edges are going, there's a hidden partition, all the edges going from the left to the right. What's the bias of this graph? It's M. Okay. It's exactly M, because every edge, every vertex is counting either all the edges as coming in or all the edges as going out, and every edge is being counted twice. And there's no cancellation going on. Okay. And so when you do half of this quantity, the summation, you get exactly M. So when bias is high, it suggests, or at least when the die-cut value is very high, the bias seems to be high. So maybe this is somehow positively correlated. Now, a remarkable thing about the bias is that it can be estimated arbitrarily well in polylog space. This is old material from streaming algorithms, This is L1 approximation of a vector in the turnstile streaming model. You have this n-dimensional vector. For each vertex, what is its bias? Initially, each vertex's bias is 0. As the edges come streaming in, you update each one of these biases by +1 and -1, linear updates. At the end, you're asking what is this L1 norm of the vector that you care about, divide by 2, but that's it. And L1 norm can be estimated extremely well with polylog n space. Okay, so this can be estimated with polylog n space. There should have been a reference here. Maybe I think this is indic. It's probably the right reference. Does anybody know any better? Okay, indic then. Okay, all right. So the neat thing that they were able to prove is that the Dicot value of any graph is at most the bias plus m over 2. So there's a non-trivial lower bound. The bias of a graph is 0. Every vertex has in degree equal to out degree. Its Dicot value is at most m over 2. Now, this is never going to give you m over 4 for any graph. Okay, m over 4, there are graphs from which Dicot value is m over 4. This will not prove it, but it will at least give you a non-trivial upper bound m over 2. Why is this bound hold? It's reasonably simple. Every vertex must lose either its in degree or its out degree towards the directed cut, because if it's on the left side of the cut, then it's going to lose all of its out degree, and it's the right side of the cut, it's going to lose all its in degree. So you're going to lose minimum of in degree and out degree, and you're going to sum this quantity minimum of in degree and out degree over all the vertices. That's exactly this quantity. Okay. So the bias is upper bounded by, or if you sum that up, that's exactly m minus this quantity. So you're going to lose at least that much. And so now they also showed that the bias is actually a lower bound on the directed cut value of the graph. Okay, and this is also not so hard to prove. So the greedy rounding. How do you prove such a result? So maybe I can try to add a page here. Okay, so let's try to, let's see if I want to try to prove this on the fly. Maybe I'll just talk about it in words, okay? Why is the bias at least the Dicot of the value of the graph? You can take your graph, and if there's a cycle in the graph, just remove the cycle and throw it out. You have not changed the bias, because at every vertex, you threw away an in degree of 1 and out degree of 1, so you didn't change the bias. So keep throwing away all the cycles that you can find in this graph. At the end, you're left with an acyclic graph. Decompose this graph into paths to take a maximal path in this graph. Okay. And here's the cut that actually is going to achieve this. You just take every vertex, and if it's got in degree greater than out degree, you put it on the left side of the cut. If it's in degree less than out degree, you put it on the right side of the cut. If it's equal, you don't care. Put it wherever you want. So look at a path. Well, it should start at a vertex which has in degree a maximal path. This should start at a vertex which has in degree 0. Otherwise, you could have extended the path. It should end at a vertex which has out degree 0, or else you could have extended it. This path is going to contribute 1 to the bias, because all the intermediate vertices are contributing 0 on this path. Again, in degree equals out degree on the intermediate vertices. And obviously, this path is starting on the left side of the cut, it's ending at the right side of the cut. Sometime it must have crossed the cut at least once. So that's the proof which says that this quantity is at least the Dicot of the graph. You put these two together, and you can always output m over 4. Every graph has a cut of size m over 4. A random cut will do it. So you know that this is a lower bound on the Dicot value, and that actually turns out to be a 2/5 approximation based on the inequalities on the board. Okay. So this is it. This is it, but it's not trivial. The fact that you can compute the bias is very, very crucial. The later paper actually improved this. They said, well, in the case the bias is relatively small, greedy is not optimal. What's optimal is you should actually round every vertex. So if the vertex has in degree greater than out degree, you decide to put it on the left side of the cut with some probability like that. So half minus epsilon. And if it's on the right side, you put it on the same probability with half plus epsilon. What is epsilon? Epsilon is the strange quantity. It does not depend on the vertex. Okay. For all vertices, it's the same epsilon. And this will actually end up giving you a 4-9 approximation. Okay. Okay. Now you would clearly look at, so a vertex has very high bias, almost all its edges are coming in, you still round it with that probability. If the vertex has 50-50 nearly edges coming in, you still round it with the same probability. You're not changing this probability at all, even though it's, the biases. So clearly this cannot be the optimal algorithm. There must be something better, but no, 4/9 is the optimal bound. And they proved that in their paper, saying you cannot do beat 4/9. Okay, so this you can do with polylog n space. This requires at least square root of n space. This is what they proved. Okay, beating 4/9 takes time. So it's really surprising that this setting that we have, you cannot do even slight improvements without using up so much space, and there are very finicky algorithms that turn out to be optimal. So this is what we wanted to generalize in our paper, and this is the kind of things that I now want to tell you about. So here are some challenges. Let me maybe say, if I want to look at a general function, I still want to have a notion of a bias, saying, oh, I gave you an instance which has where some variables have high, affinity towards being +1, and some variables have very high affinity towards being -1. What is that? Or if it's a query setting, it will be something even more. So what's the chance that I want to be +1, +2, +3, +q? And so if I have some instance, if my constraint is x and y parity z, that's a legitimate constraint on Boolean variables. Suppose that's my constraint. What would you say should be the bias of x on this instance, where x sometimes appears on the and side and sometimes inside the parity side, etc. It's kind of not clear what you're going to do. How are you going to generalize bias to this setting to get something non-trivial, if something non-trivial is possible? Then there was this thing saying, okay, why is L1 estimation useful? This actually had us for a while, but actually this turns out to have a very nice answer. L1 estimation is optimizing a Boolean constraint, okay? I give you some vector, arbitrary label vector x1 to xn, and I want to compute its L1 norm. What is it? It's just the maximum over all AIs in ±1, summation AI xi, some linear form. Okay, so this is maximizing over a space of n Boolean variables, some function. So the fact that you can maximize some particular Boolean expression is clearly useful, and we were able to use it to do a die-cut approximation, because we had inside it a routine which was doing a natural Boolean optimization. Does this make sense? What could be a generalization? This had us for a while, and then finally we got an answer. So let me just tell you right now what this. In general, what we will be thinking about is some matrix. So what was this x1 to xn? Maybe it was the biases of the n variables. Imagine you had some matrix which said, oh, a variable wants to be +x1 with some probability, or maybe it wants to be the -x1 is the affinity that it wants to be the negated value, okay? And what we are doing over here in the L1 approximation is we are saying, okay, let's find a way to pick one entry from each column so as to maximize the sum. Yeah.
So in the graph setting, could bias be like if you flip the vertex from the left to the right, what is the worst regret that you could get?
That's great. Yeah, yeah.
So can't there be a regret with respect to flipping a variable here and then using that as the proxy for bias?
Right, but then, in some senses, when you have an expression sitting inside a more complicated form, it's possible that there are some places where you feel there is no need for a local bias, but if everybody feels this way, if the constraint is just parity, nobody feels, that they're responsible for the decision at hand. At the same time, nobody, you could either go one way saying, oh, look, anytime I will flip, I'll also have a pair who will flip, and then that way we'll make sure that we actually don't influence anything, or every time I change, I'm changing everything, but then it's not clear which direction you want to be. So a priori, it's not clear to me what should have been the right measure of thing. In fact, up to this date, I don't know. I mean, we have actually some bias for this function f, which is the best bias that you can use to distinguish something in something. I don't know what it is. Okay. I actually don't know if this particular function is approximable better than random or not, but there exist such functions. In those cases, I don't know. Yeah.
So in the dichotomy settings, what bias is supposed to say what, like how much do you expect, like if you shift the vertex from one side to the other, and how much do you expect it to change the value of the dichotomy? Like
It's not, I mean, it cannot be purely local because sometimes just changing one variable on its own may not make a difference. It's changing many variables together that's going to make a difference. So if I would suspect that, I mean, it's conceivable that there exist problems where each variable on its own cannot make a difference, but because of this cumulative effect, changing it along with other variables is going to help do better. So it's not totally clear.
Very nice question. So this L1 equal to this maximum, this representation that you have, does it, and I guess AI are just minus 1 or plus 1 here, right? They just take two values.
Yeah.
Does it generalize in some for LP in some sense, or you allow AI to be?
LP, I don't know actually at all. And the right generalization for our setting does not turn out to be the LP norm. Instead, what we are doing over here is we are saying, okay, look, if you have a query assignments, and I don't know which one of the Q things to want to prefer, but I have some sort of a thing saying, if I take this value, I have some preference. I have some preference for the ith value and some preference for the jth value, etc. I'll write this down as a matrix, which is a Q by N matrix. And the first variable has these Q different preferences. And the second variable has, each variable has these things. And what I'd like to do is to say, well, how can I optimally pick each one of these columns independently so as to maximize the preference? That thing turns out to have a name. It's called the 1 infinity norm of a matrix, apparently. And norm computations in the streaming setting, they've been extensively studied. This one has also been studied. There's a paper of Andoni, Krauthammer, and Onat probably, which computes this with polylog n space. Okay. So yeah, if somehow you could take your instance and massage it so that each variable is sort of expressing a wish, saying, I want to be this value with some preference and this value with some preference and that one with some preference, I can assign to each variable the maximum preferred value and use that. Okay, and so this could be a proxy for the back bias. So now the question is, okay, what can we do? So let me first give you a completely trivial thing. Yeah.
Then that 1 infinity norm. So what is there in the purple matrix that you have drawn at the bottom? Then those are real numbers?
Yeah, these are all good. Let's work with non-negative numbers in this matrix, okay, just to make sure negative things are not, I would want at least the maximum entry of each column to be non-negative, okay, to at least simulate that setting. But let's pretend every entry is non-negative. Okay, does that answer your question?
And then just take a transversal maximizes the.
Yeah, so you're allowed to pick one non-zero entry in each column and sum up those values.
It's like you create a row vector based on the infinity norms of each column,
Right.
and then take the L1 norm of that vector.
Exactly. Yeah, it's L1 norm condition, the fact that each entry is non-negative. Yeah. Yeah. Okay. So this is the graph that this is some norm thing that we can actually use, and this is going to be good enough for the query setting. So there's still these questions. What do we want? So this is roughly our abstraction of the previous algorithms. For every variable, we are going to maintain some notion of a preference or a distribution, I'm calling it, but it's non-normalized, so it's a non-negative preference for every value, so this will be a preference saying di of sigma will say what is the preference that the ith variable have for taking on the value sigma. And the only thing we're believing about this di's is it's monotone. If di of sigma is larger than di of tau, we would prefer to give it sigma than tau. But exactly how much preference to sigma over tau, we don't know. We don't know what the algorithm is going to ask, and we don't actually have a real idea how to do the rounding analysis at all. So we're going to take the simpler problem of this distinguishability, at least gamma satisfiable, at most beta satisfiable. We'll try to just solve that by some amount of luck. Okay. So what's this idea? So we're going to guess and fix some weights, saying, look, I don't know how much preference to give to x appearing as the first variable of f, or if it appears as the second variable of f, or if it appears as the third variable of f. Maybe I can just maintain an entire matrix saying x appears, so many times as the first variable, so many times as the second variable, so many times as the third variable. For each one of these appearances, there's maybe some conversion factor lambda sub j sigma, which says if I'm appearing as the jth variable, my preference for being assigned the value sigma is so much. If I'm the jth variable and I want to be assigned tau, lambda j tau will tell me what this value is. And these lambda j sigmas are all non-negative also. So somehow we're going to guess this thing. It's going to be guessed once and for all for a family of functions. And after we're done, we're done. We're just going to maintain these lambda j sigmas, and each time a constraint comes along, I say, okay, I've now found a new variable which has appeared as the first variable. So update its preference list by lambda sub, the first variable's name should be updated by lambda 1 sigmas. Okay. And then the second variable preference should be updated by lambda 2 something. So there is this matrix that we are building, Q by N matrix, and the preferences are being updated. Yeah.
This is some sort of an offline algorithm which you're going to streamline eventually.
Exactly. That's the right way to think about it. It's an offline algorithm. It's going to maintain all these things, and then at the end, it's going to compute some number, and we're just going to say, how can I compute that number in the streaming fashion? But this is a matrix. This matrix is being updated linearly. At the end, I'm going to do some norm. So one can believe that matrix norms can be computed and maintained in this turnstile fashion. So that makes it all very believable that this is work. So there is this lambda j sigmas that we're going to work with. We don't know what these lambda j sigmas are. So we're just going to hope. Here's the theorem that I'm going to claim, and it's a very fishy theorem. So we're just going to say, okay, look, if it turns out that there's some lambda j's in tau, such that whenever I consider an instance who's a good instance, and I look at what's the maximum, when you maximize over each variables and say, what is your preferred value, and take that assignment, it turns out you get a maximum value, which is at least tau. On the other hand, whenever you're working with a beta satisfiable thing and you compute the same quantity, it's at most strictly less than tau. Then you're done. Okay. But this is just wishing the problem away. If there is something nice, then you can solve the problem efficiently, because you can compute this di sigmas in a streaming fashion and compute this maximum assignment in a streaming fashion. Why should this exist? And if it doesn't exist, what would you do? Okay. So, and a priori, I'm looking at infinitely many instances over here, any number of variables, any number of clauses. Anytime you have a value which is at least gamma, and gamma is an absolute number because you've scaled it, so it's a fraction of things. Then you should have this condition. So how can I even verify that a given assignment to lambda, say j sigmas and tau, satisfies this property? So the main theorem I would say in that paper is that this criterion is actually decidable. Okay. And that's all maybe that I'll try to prove. I'll say a little bit about what happens if these things don't exist. Not only, so if there is a gamma and beta can be separated by some lambda j sigmas and tau, then we have an algorithm for distinguishing gamma from beta. If it doesn't exist, what happens? Well, then we'll come up with a lower bound actually, just based on the fact that these things cannot be separated. There'll be a thing saying every sketching algorithm will require square root of n space. So we have no idea what these lambda j's are, what gamma and what beta for which it works, at least right now. But if there is an algorithm, it's going to be of this type. If there is no, and if this doesn't work, there will be a lower bound and we can prove it.
So there's an I, it's an if and only, and why is it important that the criteria is decided?
Why is it important? Well, okay. Yeah, I mean, right now if it's an if and only if, then already the criterion being decidable is not important. But the criterion, I mean, you know, it seems very, very, you know, unmanageable. How do you even look at this thing? It's almost like asking the question, is there a fast algorithm for this problem? And if there is a fast algorithm, then there's a fast algorithm. We don't want something as tautological as that. So just to say, well, actually, this is a sentence that you can make a meaning of and actually come up with an algorithm for it. So how are we going to do this? How are we going to decide this? The key idea over here is that the instance, actually, what can an instance look like? I mean, you suppose you want to create instances which have gamma satisfiable things. How would you come up with it? Let's take gamma equal to 1, 100% satisfiable. How would you try to come up with such an instance? Okay. And there's a kind of a very natural idea. You just plant a solution in an instance and then just use it. Okay. And what is it that algorithms that we know can maintain? They can try to sort of look at every variable and probably, I mean, they can't completely do this, but somewhere implicitly we are saying we seem to be able to maintain statistics of the form. How often did this variable appear as the first variable in the constraint? How often did it appear as a second variable in the constraint, and so on? It's a k by n matrix that we are able to maintain. So this k by n is our statistics of the input instance, that somehow the streaming algorithm is not quite able to do that, but morally that's what you're able to do. In the die-cut case, you were able to say how many vertices had 100% edges coming in, how many had 50% edges coming in, how many had negative 100%, 100% edges going out, etc. Okay, so these kinds of statistics you're able to maintain. So we want to make sure you fool these statistics with your instance, but this instance should be 100% satisfiable. So you, on the one hand, 100% satisfiable, some statistics. On the other hand, beta fraction satisfiable, same statistics. If you get the two, then maybe you can fool this algorithm. If you don't get those two, then maybe there's a way to run this algorithm. So that's roughly what happens. So we looked at this thing and said, okay, how would you try to create an instance which has 100% things? And say, well, okay, let's fix an assignment A1 to AN, and now only use constraints satisfied by A1, this vector A. Okay, so only apply a constraint if it's satisfied by this thing. That's easy. This is going to generate something for you. Now, how would you go around making a bad assignment, by the way? So this is how you go for, opt at least gamma. If you want opt at most beta,
generate constraints that are satisfied by the underlying function has been fixed, and we're just deciding on what variables to plug.
exactly.
To make that function.
Yeah. So think, for instance, you have one function, and we're going to apply this function to triples of variables, maybe. So how should I apply this function to which triples of variables should I apply it to? I might not apply it to all the triples that it's applicable to, but I might, for each, I pick a triple and I say, should I apply my function to this, or should I skip this constraint? I'll apply this function if this A satisfies it, and if not, I won't. At the end, I will only output a set of functions in the constraints, but I won't tell you what A is. And you have to determine if the A existed. This is how I built that graph, by the way. Earlier, I had a cut in mind. I sampled edges which were satisfying, which were going across the cut, and gave them to you.
So it's a pretty random condition on A being
at least for now. Yeah, at least for now. And I'm not so worried about the randomness. We'll get to that in a moment, but that's roughly what we're going to do. For the other side, it's not good enough to say, I have an assignment in mind and pick variables which will, pick constraints which will fail it, because there might be some other assignment which is actually doing very well. So what you have to say is, look, okay, I will somehow, I mean, you've somehow come up with an instance which is beta unsatisfiable. I'll try to say somehow that you don't need to use so many variables to get the same statistics. Okay. So what does it matter in this assignment that you picked? All that matters is how many of these variables, I mean, if you have an instance, you don't have a satisfying assignment in mind, of course, all you're going to give me is an instance saying these are the constraints. If these are the constraints, then, and you can only satisfy beta fraction of them, let me apply the same constraints on the same instance after I permute the names of variables. Still only beta satisfiable. Take the union of these two constraints, still only beta satisfiable. So I can do all these permutations and maneuvers, and at the end, really what will happen is that I come up with a much more succinct thing. I don't need to use too many different variables for this part to create a, so for the negative instance, the insight is, if you want to fool the statistics of any algorithm, you don't need lots of variables, because at the end, you'll be applying these constraints that you have to all permutations of these variables subject to some constraints. So the things that you care about is, of course, if I want to match the statistics of the yes instance and the no instance, then if these variables appear only as the first variable in constraints, then I would like to have the same number of variables appearing only as the first variable here. So these statistics need to match. Okay. So what we ended up doing in this thing was saying, okay, look, we are going to actually come up with a very carefully chosen, so Q by K. Okay. So I'm going to start with instances on only K times Q variables. And in my head, the planted assignment is each variable is assigned its value, which is equal to its row number. Okay. So that makes a lot of sense. And every constraint will pick one variable from each column. So the ith variable in the constraint will be the ith from the ith column. Okay. So this is the class of instances that I use for my yes instances. Okay. And now I can get any gamma that I want, because I take a random constraint, I pick a random satisfying assignment for this constraint maybe, and I say, okay, I know which variable that I want to use for this thing. So even if gamma equals 1, I can build this up. Okay. And if if I'm given other choices of gamma, I can still do it. I can just pick some distribution. So at the end, what does an instance look like? An instance looks like a distribution on Q to the K. Okay, because I pick a random constraint, but a constraint says pick somebody in the first row, picks a column, pick somebody in the second column, pick somebody in the third column, etc. So a yes instance maps to some distribution, and a no instance, I will use the same set of variables Q and K. I will follow the same constraint, which is K times Q variables. Exactly.
Although that Q is no more the alphabet. It used to be alphabet.
Oh, it is still the alphabet. It's still the alphabet.
That many variables nevertheless.
Exactly. Yeah. So we are using Q times K variables. In the planted assignment, every variable takes on its assignment, which is its row assignment, and this will be guaranteed to satisfy gamma fraction of things. In the no case, what I will do is somehow pick up some assignment and pick up some instance, which will still be viewed in this way. The instance will always have the ith variable from the ith column. In every constraint, the ith variable will come from this column. Okay. So this instance also looks like a distribution on Q to the K. Okay. And by the way, when should I stop? 5 minutes. Okay, sounds good. So the yes instance looks like that. The no instance looks like a distribution on Q to the K. in the no instance, I'll have to do some offline calculation to make sure that no matter what assignment you pick, you cannot satisfy too many clauses. But this is something, I mean, so notice that if I give you a no instance, that is a distribution. If I'm searching for the space of all no distributions, I'm searching in the space of all distributions. And then I have to see how much can you satisfy in this. But for each, if I fix the distribution, determining how many constraints can be satisfied is some brute force search, some finite size search. So there's a constant number of real values, and then some constant amount of computation. So hopefully this is all decidable, and indeed it turns out to be decidable in space poly in Q and K. Okay, so space which is polynomial in Q and K. So I can ask this question: okay, is there an instance on these variables which satisfies the constraint that every constraint ith variable is from the ith column, and no matter what assignment I pick, I satisfy at most beta fraction? But actually, I'm going to think, if I was just going to insist that no assignment satisfies this much, I won't get such a rich thing. Instead, what I'm going to insist on is no symmetric assignment satisfies this many constraints. So what I'm going to think of it is, okay, here's this instance, but I'm going to lift it into an instance on n variables. How do I lift it to an instance on n variables? I'll pick many copies of, I'm trying to think whether I should go column wise or row wise. Think I want to go probably column wise, I'm not sure. Okay, so let's say there are going to be n times k matrix. And when I decide that I'm going to apply a constraint here, no, okay, sorry, that was wrong. I want to make this, yeah. So imagine I'm thinking of a big matrix over here, each variable, there are q things here and n things there. When I find a constraint over here that I want to apply, I'll pick a random column and map it to this thing, a random column and map it to that thing, and a random column and map it to this column here. Okay. So when I do this lifting, it's not like you get to choose a arbitrary assignment to variables over here. You have to fix some assignment to these q times n variables, and they have to satisfy lots of clauses that I have chosen randomly after you've fixed the assignment. If they don't, and if the probability that they satisfy too many is sort of exponentially small in the number of variables, then I can run a union bound on this thing. So it suffices to satisfy a weaker constraint which says any symmetric assignment to these variables will not satisfy too many constraints. By symmetric assignment, I think what I mean is that in a particular row over here, you get to say what is the distribution, some distribution over query space, and that's what you're going to use, but you're going to use the same distribution for all the variables that appear here. So, and I'm going to pick the assignment at random for all of these variables. That somehow emulates the fact that over here, you picked some assignment, and then I'm applying constraints at random. Okay. So anyway, so there's some criterion which says this is how I'm going to build the no instance or analyze the no instance. And these are both distributions on Q and K. The constraint that we had earlier saying, oh, we can measure some statistics on how often which variable appeared in which position corresponds to saying you can sort of measure some distribution, the marginals of this distributions on Q to the K that you have. What's the probability that the first that this distribution picks this variable as the first variable, or this variable as the first variable, or that one as the first, as the ith variable. Okay, so you can measure the marginal, but you don't really get to measure the correlation, saying, oh, between this column and that column, what's the chance that if this appears as the ith variable, what does it appear as the jth variable? This is not the kind of statistics that would be like saying in the die cut, how often do edges go from high bias vertices to low bias vertices or something? We don't measure that. All we measure is for each vertex, what's the fraction of vertices which have 90% edges coming in, 20% edges coming in, etc. So that's equivalent to saying these marginals should match. If the marginals can be made to match, this sounds like bad news for our algorithm. Our algorithm won't exist. We build a negative result which says, okay, this we can use as a gadget for a lower bound, and now we use communication complexity, etc., and prove that this problem takes at least square root of n space to solve. If the marginals do not match, that turns out to be exactly this criterion that I asked for earlier, which was that, yeah, if the marginals do not match, then these things do exist. And so now you have an algorithm. So that's the entire story. So there is this mysterious algorithm. It actually works in all cases, completely rules out sketching algorithms when the technique doesn't work. And when the technique works, it gives a sketching algorithm. At the end, it's still, we have like some polynomial amount of space computation, which can say, okay, look, if you want to understand what max k and complexity is for k equal to 7, well, there's something that will run in time 2 to the 7 and 2 to the 2 to the 7 maybe or something, and tell you what is its approximability. So that's the main result. There is, by the way, for the special case of max kn, there was a work done with by a bunch of undergraduates with Santoshini who were able to say that actually for max kn, here is a precise expression that actually works. And proving that involves a lot of extra analysis and some very fortunate coincidences about how these things worked out. But in general, yeah, I mean, I have no idea which problem is going to have what kinds of algorithm, but the algorithm is from this space. That's all we can say. All right, so I'll stop here. Yeah.
So, I mean, typically in CSPs, there's this kind of like random versus planted paradigm, right? So, is that understanding of when that's useful here? Is it useful at all? From low bounds.
Right. Yeah. So the nice thing over here is that these are unconditional results. We're not even, I mean, we're definitely not even assuming P not equal to NP or something, but not things like sum of squares hierarchy at level I will fail or something like that. So it makes some sense that when you get these kinds of unconditional results, you get to understand the distribution, which makes it hard, and you get to know exactly what's the limits of the thing. The fact that we had to work with planted algorithms here, I think it's planted relative to what you can measure, right? So it's the same story with maybe other settings, but in say in the unique games and sum of squares settings, people typically try to plant an assignment subject to the, plant an assignment and then say, well, the statistics that sum of squares algorithms can measure are not useful for the planted versus unplanted setting. So there's this extra work that they have to do. Here we said, well, let's fix the algorithm because we think this is the one that's optimal. Go for the planting, which makes this algorithm useless, and then try to say, well, okay, this algorithm is useless, but is there something which proves something broader? That part was, I think, different. Obviously, a lot easier because we're working in, at the end, you're proving one-way communication, complexity, lower bounds. So it's much easier in that sense.
So the final algorithm is not a linear programming relaxation because there is products of delays involved in each one.
Okay, good. So to decide whether one of these, I give you a function family and then you ask, and a gamma and a beta and ask the question, can you decide if gamma versus beta is solvable? This thing, it's not linear programming, no. It's intuitive that it's convex because it's, it's distributions and blah, blah, blah. But actually these convex things do have non-linear surfaces. In fact, we even plot the optimal gamma versus beta for die cut, which was not something that the previous work had done. For every gamma and beta, can you solve this gamma beta problem with die cut or can you not? And that thing itself has sort of quadratic surfaces in there.
So given the lambdas, given these lambdas, it's still the final algorithm is, so if I just forget about streaming and just
Good. Okay, sorry. So no, once you're given the lambdas that will work for a particular family F, the rest of the algorithm is simple turnstile updating of this matrix and then computing this thing. And we are just going to, so at the end, it's just saying, okay, your optimum is at least gamma or at most beta.
Yeah.
It doesn't know what the satisfying assignment is, but that's inevitable. You don't have space to remember the instance and the assignment. So all it says is yes, it's satisfiable or no, it's not. And the way it determines that is just by saying, okay, is the bias value at least this much or at most that much.
And so, and is the decidability proof somehow implicit in it? Is the claim that if you take such a lambda J, takes the algorithm and it's somehow just check brute force it works for all instances to some finite size, then it works for.
Right. So that would have been well, okay, that wouldn't completely work because we are looking at all weighted instances. Every constraint gets a weight because the price we pay for compressing to KQ variables is I might have to use the same constraint multiple times and then it becomes a weighted thing. So there are a bunch of real numbers that you have to work with. And once you work with a bunch of real numbers, you just go into existential theory of reals or something. It's like 2 or 3 levels of quantifiers in the quantified theory of reals.
The difficulty of extending this to general streaming.
Okay, that's a great question. So the question was, what's the difficulty of extending the lower bounds to general streaming algorithms? First, the truth value might be an obstacle. I don't know that the correct answer is yes, there is no other algorithm other than the streaming one. There may be other streaming algorithms, but they're not any sketching algorithms. The way we found out, unfortunately, was by posting a paper which claimed the streaming lower bound and then getting feedback saying you have a bug. At this point where you say that this variable condition on that is distributed identically to that, oh, the conditioning doesn't forgot the conditioning also affects the right-hand side, and oh. So it looked like a tiny little error, but it just sort of bubbled all the way up. And at the end, there was, for the class of instances that we were working with, there are algorithms that are not streaming algorithms which can distinguish them. Okay.
Not sketching.
Not sketching algorithms, but they're streaming algorithms which can distinguish them. They're log n space streaming algorithms. They run tiny random walks on the instances. So we don't know what the hard instances might look like. We don't know how to prove these lower bounds. And for all we know, I mean, a lot of the things, when we first wrote this paper, we thought we had the streaming lower bound, we had the square root of n lower bound, but we completely believed that everything would just work exactly the same way for linear space. It just, monotone upwards, we just have to work much harder. It turns out every possible fork has, it seems to be open at this stage. Yeah.
So you mean like there's no n to the omega 1 streaming lower bound in this one?
N to the, right. So streaming lower bounds, we don't have an n to the omega of 1, which would be great. I mean, I think it would be something that will explain a lot. On the other side, we believe for many problems, between n to the 1/2 and n to n, there should be algorithms out there, but we don't have any proofs of those. There are, there may be some restricted cases where we might have some guesses on algorithms, but yeah. One thing that we can say right now is at least, the algorithm of the lower bound for max cut, at least the square root of n space lower bound used to be on randomly ordered instances. So in fact, the graph that you produce in the no instance was a random graph. The yes instance was a planted graph with again randomly ordered edges. Just randomly generate edges from the planted model. We now know that actually with random ordering, many of these statements in the dichotomy are failing. So you can actually get algorithms for die-cut which are better than 4/9 if the edges were ordered randomly. So you really needed worst case ordering over there and so on. So a lot seems to be very fragile which is a bit surprising to us. Yeah.
Clap again.
Okay.